Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference. Case, Crude Oil Scheduling and Refinery Planning. This case is based on the document Crude Oil Scheduling and Refinery Planning by Lagrangian Relaxation. Both crude oil scheduling and refinery planning are formulated as optimization problems, and are integrated into a single full-space MILP. The integrated formulation is constructed based on the overlap between the CDU charging operations in the scheduling level, and the CDU feeding decisions at the planning level. And MILP priority slot-based continuous time crude oil scheduling formulation, and a multi-period discrete time NLP refinery planning formulation are used. A multi-scale framework has been proposed to integrate different time representations. The mathematical formulation for the full space problem is developed in 3 stages. Multi-period discrete time formulation for refinery planning, RP, maximizing the total NPV. Priority slot-based continuous time formulation for crude oil scheduling, CS, with multi-period extension, minimizing the total crude purchasing cost, and set of linking variables and constraints of crude oil feedstocks between crude oil scheduling and refinery planning, with the objective maximizing the total NPV minus total crude purchasing cost. The custom indicates that the most common position, when formulating a mathematical model, is an integral formulation, full space, which brings together in a single formulation all the equations that define the problem. This corresponds to a top-down approach. In this case, the model could be called Crude Oil Scheduling and Refinery Planning Model. However, considering the evolution of computational power and algorithms, today in ascending formulation, it is indicated that starts from the atoms, that is, from the basic parts of the problem. This corresponds to a bottom-up approach. The case presented is a good example of this approach, dividing the problem into 2 formulations, Crude Oil Scheduling Model, and Refinery Planning Model. These formulations are integrated to form the holistic model. The Crude Oil Scheduling Model represents the first part of the process. This type of scheduling problem is usually formulated as continuous time models, which facilitates the coordination of activities exactly, at the instant level. The Refinery Planning Model is more oriented to the use of discrete time formulation, since it involves the planning of activity volumes in multiple process units by periods. Proper handling of these 2 formulations is easier under the divide and conquer approach. The graph shows the flow rates in the simplified refinery planning example. The goals of the 2 models are crude oil scheduling. The goal is to schedule crude oil transfer operations, with a certain limit for ship unloading capacity and tank transfer, and refinery planning. The goal is to optimize the amount of crude oil and intermediate flows, with working modes and capacities given for the CDU and the refinery process units, where the total benefit of the final product is maximized. The crude oil scheduling model is a continuous time non-convex MILP model, based on priority slots. Its main features are given vessel arriving and leaving time, tank inventory management, CDU charging continuously through time, and non-overlapping inlet and outlet transferring. The key variable is the binary variable ZIV, that represents the assignment of the V operation to the property slot I. The key constraints are, time decisions in each time slot must have consistency, non-overlapping operations not in same slot, non-overlapping time decisions are ensured by big M type of constraint, nonlinear crude composition constraint, for each slot I, crude C, and outlet operations V, and other mass balance constraints. The objective function is the crude cost. The crude oil scheduling model is a continuous time non-convex MILP model, based on priority slots. Its main features are given vessel arriving and leaving time, tank inventory management, CDU charging continuously through time, and non-overlapping inlet and outlet transferring. The key variable is the binary variable ZIV, that represents the assignment of the V operation to the property slot I. The key constraints are, time decisions in each time slot must have consistency, Non-overlapping operations not in same slot. Non-overlapping time decisions are ensured by Big M type of constraint, nonlinear crude composition constraint, for each slot I, crude C, and outlet operations V, and other mass balance constraints. The objective function is the crude cost. The integrated problem, full space problem, is a non-convex MILP. The integration process is linking constraint, defined as the equivalency of CDU charging operations and CDU feeding operations. Full space problem, MILP model containing scheduling, planning and linking constraint of CDU feedstock, and multidimensional approach, different time representations. Coordinate planning and scheduling starting and ending times. The design of the refinery configuration is based on the figure. 3 raw materials, associated with 3 vessels, 3 storage tanks, and 3 cargo tanks, are the upstream operations for scheduling. Zone A. In Zone B, there are several process units such as hydrotreaters for light cracked naphtha, LCNHT, coker light naphtha, CLNHT, and diesel, DHT, fluidized catalytic cracking unit, FCCU, delayed coker unit, DCU, stabilizer unit, stabilizer, catalytic reforming unit, CRU, and delayed coker, DCU, are the downstream operations for planning. The distillation unit is composed of 5 towers, a flash distillation tower, flash, 2 distillation units, CDU1 and CDU2, a vacuum distillation unit, VDU, and a debutanizer unit, debut. 3 blenders for gasoline, blender, diesel, blender, and fuel oil, FA blender, are installed in the refinery. Zone C. The graph presents the crude oil scheduling data. The graph presents results for 3 planning scenarios, 12, 24 and 48 days. The graph presents the results of the planning, by groups of 12 days, in 48 days scenario, for the different finished products produced by the refinery. 3 different solutions approaches was studied. Monolithic approach, solve full space model by using state-of-the-art MILP solvers. Hierarchical approach, solving sequentially the 2 sub-problems CS, crude oil scheduling, and RP, refining planning. There are 2 possibilities. The proposed is solve planning, fix CDU feed, and solve scheduling, and Lagrangian decomposition. For the monolithic approach, the different alternative solutions come from the state-of-the-art MILP solvers used. For the hierarchical approach, the sequence of solving the 2 sub-problems CS, crude oil scheduling, and RP, refining planning, is a key decision. Both methods are tested in 3 cases and the computational results are presented in Table 10. The 2 options are stated as scheduling planning and planning scheduling, which explicitly represent the sequence applied for solving CS and RP. The objective value is determined by the sum of the individual CS and RP objectives. This process could be improved if cycles are incorporated to achieve convergence. Which can be considered as a primal dual algorithm that uses an improved subgradient formulation for the dual problem by exploiting a trust region approach. Because of the non-convexity of the problem considered here, strong duality is not guaranteed, and therefore there might be a gap between the global optimal solution and the Lagrangian dual, which this algorithm may not be able to reduce to 0. The overall solutions of the 3 cases, 12 days, 24 days, and 48 days, are presented in the table. The objective functions for both monolithic and Lagrangian decomposition approaches are larger than for the hierarchical approach, 75%, 60%, and 6%, for the 12 days, 24 days, and 48 days cases, respectively, corroborating their advantage. Moreover, the proposed LD approach requires less CPU time converging to a small, 1% to 5%, optimality gap, when compared to the monolithic approach using state-of-the-art MILP solvers. The graphs present the computational results of bounds versus iteration number and CPU time. The graphs compare the Lagrangian relaxation method using Dicopt versus the Barron global algorithm. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.